this parent function, y equals 10 to the power of x, okay, we can plug in, oops, not writing, negative 1, 0, 1, and 2, because all of those can be exponents. So this is more like the functions that you did before, that you get to kind of just stick with those numbers. Now, when you plug in negative 1, that means that you're calculating y by figuring out what 10 to the negative 1 power is. So what's 10 to the negative 1 power? 1 over 10. Okay. And then when you plug in 0, you're calculating that y value by calculating what 10 to the 0 power is, which turns out to be 1. And then 10 to the first power gives us 10, and 10 to the second power will give us 100. I'm not going to plot that point, but I have it there if I needed it. You could. You do it, okay? Because you numbered your axis differently, it'd be okay. All right, so if we plot these, okay, we have negative 1 is at 1/10, so it's like just barely above the axis. We have a point at 0, 1, we have a point at 110, and then we would have a point at 2, 100, way up there, okay? Now, just to give you an idea of what happens so we understand thoroughly, I'm a little confused. I get right here, this is going to keep going up, up, up. What's going to happen when it goes right here, okay? So let's think about if you plugged in negative 2, what would you get? What is 10 to the negative 2 power? Yeah, 1 over 100, right? What about if you plugged in negative 3 as the exponent on 10? 1 over 1,000. And then like negative 4, you'd have 1 over 10,000. This number is getting closer and closer to being what? 0. But is it actually ever going to reach 0? No. So kind of a lot like that crazy chart that we did when we did our rational functions, right? It's getting really close to something but never becoming it. So in these functions, we have an asymptote right here at y equals 0. Okay? Because the y coordinate is getting closer and closer to 0 but never hitting it. And that means the behavior of this graph looks like this. Notice the relationship here between our log numbers. We were plugging these in last time, right, and getting these out. So the reason I think the exponential ones are easier is we're used to being able to have the really nice numbers right here for x and then figuring out what y is. So these will work like this every time. These will be consistent like your other parent functions. Yeah, Christian. Yes, so we're always going to have this asymptote at y equals 0 for any parent function. So the only way that that's going to change is if we put in transformations, like we do when we're graphing. What kind of transformation is it going to take to move that asymptote? What would we have to do to our graph to get it to get this asymptote in a different place? We get a vertical shift, something with y, right? We're going to have to add or subtract stuff to y to get it to move. So just like yesterday, or 2 days, 3 days ago, whatever, we had to add or subtract to x because our asymptote was here and only horizontal stuff was going to move it. Now our asymptote's here and only vertical shifting up and down will move it, okay? So are we okay with how to build the parent functions? Yes? All right, so go ahead and on your paper with your groups, build your parent functions for the next 3 exponential functions. So you should be able each time to plug in negative 1, 0, 1, and 2. That's what makes these a little simpler than the logarithm ones. Okay? Okay, so quick check. If you haven't got to a certain one, then make sure you fill in what we get. If you did all of them, make sure it matches with what we get up here. So again, because with exponential ones, I can choose what I want the exponent to be. I can plug in whatever values I want. So I start with these. And then this is what you should get with a base of 2. 1/2, 1, 2, and 4. Okay? So then your graph should look like this. Okay. So something like this. And you still have an asymptote here at y equals 0. Okay? So a lot like the log functions, Each parent's a little bit different. They have the same kind of shape, but they grow at a different rate. Like the points go in specific places that are slightly different. So then if we do, does anybody still need this one? All right, so if we look at 3 to the power of x, again, we should have plugged in negative 1, 0, 1, and 2, and that should have given us 1/3, 1, 3, and 9. Okay? And so again, your graph should have looked the same shape, but points just in slightly different places. And still an asymptote at y equals 0. Any questions on our 3 to the x graph? Okay, so the last one was 1/2, and we saw with logarithms that when you used 1/2, because the base was smaller than 1, the shape was still the same, but possibly turned a different direction. And so you kind of see that same thing happen here with exponential functions. So we can still plug in the same points. Okay? But 1/2 to the negative 1 power is 2. Then we would get 1, 1/2, and 1/4. Okay? So what we see here is something like this. But again, you still have this asymptote at y equals 0. So everybody okay with our parent functions? A little easier than logarithms to build the parent function? Okay. All right. So then we want to just do the same thing that we've been doing in order to do the transformations for the graph. Okay. Oh, that's not good. Hold on. Okay, so turn it over on the back. Again, 2 examples. Okay. So here's my function. That means that the parent function is y equals 2 to the x, because it has a base of 2. So one thing that students confuse often, because we're used to pulling out all the numbers in here and saying they are some sort of transformations, is that people go, oh, there's a vertical stretch of 2. No, okay, the vertical stretch is in front of the 2. The 2 is the base of the function, and the base is part of the parent, okay? So you really have to make sure that you don't count this as a transformation. If you originally saw that and that's what you thought, you might want to make a note for yourself on your notes that this is the base and is part of the parent function, so you don't confuse it with a transformation. So if you recreate this parent function, so we talked about, I know you have this on the other side, so you guys could look at it and use it. If you're taking a quiz or test, you're expected to be able to graph this, and so you're going to make the parent chart yourself. But again, you'd make it like we just made them. You'd pick negative 1, 0, 1, and 2, and you'd think about what 2 to each of those powers are, so 1/2, 1, 2, and 4. So you'd have your parent function. Okay, there are some that you're going to use so often in the homework that you might end up memorizing, but you can't memorize infinitely many. So we have this. Our transformations. Okay, let's practice writing them so that you guys can identify them when you need to. This does what? This 3. It multiplies to the y, and what's the name of the transformation that's happening? Vertical stretch. Okay, right? So there's a vertical stretch. Okay, we already talked about the 2 being part of the base. What's this plus 2 right here? Okay, it shifts it left 2. And then this minus 1, down 1. So these 2 that I put points next to are vertical, so those things are going to affect our y. So our y is going to get multiplied by 3 and then shifted down 1 or subtract 1. And then the horizontal one right here, left 2, means I'm going to subtract 2 from my x values. So I'm going to take this column of x values and subtract 2. So negative 1 minus 2, 0 minus 2, 1 minus 2, and 2 minus 2. Then I'm going to take my y values and do this calculation. So I'm going to times 1/2 by 3. So that's going to be 3/2, and then I'm going to subtract 1. Okay? So if you don't know what that is, That's 1 1/2 minus 1, so it's just a half. Or if you did it by turning it into fractions, okay, you'd turn the 1 into 2 over 2, so you have a common denominator. But either way, you'd get 1/2. Okay? Then I'm going to use 1. 3 times 1 would be 3, minus 1 would be 2. I'm going to use 2. 3 times 2 would be 6, minus 1 is 5. And then I'm going to use 4. 3 times 4 is 12, minus 1 is 11. And then we also want to remember we have an asymptote here. For our parent function, what's the equation of the asymptote? Y equals 0. Okay? If you forgot, look back at all the ones that we graphed on the other side. They all had the same asymptote. Notice it's y equals 0. Horizontal lines are like that. You would have to change the y coordinate of all the points to shift it. This is getting shifted down 1, so I know my asymptote will move to -1. If you're confused, notice that the asymptote has a y here. Do everything to this number that you did to everything else that was a y coordinate. Okay? That your asymptote would be 3 times 0 minus 1. The 3 times 0 part doesn't change it from 0, but then the minus 1 would make it at -1. So that your asymptote is at y equals -1. So we would have our asymptote at y equals -1. And then if I plot these points, I should get something that looks like an exponential curve. So -3, 1/2, -2, 2, -1, 5, and then 0, 11 would be like somewhere up here. So the curve goes something like this. I know it goes below the x-axis because my asymptote is down below that. And remember, it's getting closer and closer to that asymptote, infinitely close to it. So I know it crosses at some point. I might not have been accurate in where it crosses because I didn't plot anything that was exactly the intercept. Yes, Abigail. Sorry, y equals -1. But I plugged 0. I basically did this with the 0 that I originally had from the asymptote. So originally, my asymptote is related to y, and it's a 0. So I'm saying you could just, if you were confused on what to do, you could plug it in like you did with all your other y's. And same with the log ones. It was an x equals something. You could take that 0 and plug it into your x transformations and get the new asymptote just like we did here. Okay. All right, are we okay with this idea? Any questions on the graphing part? Okay, so then let's look at the intercepts. I need to change the page and I can't see the equations. All right, I'm going to do the intercepts on another page because I wanted it to be so that we had more room. So for your x-intercept, you guys have boxes for it on there. So for your x-intercept, we set y equal to 0. And then we solve this equation. So now you have to go back to the first kind of solving review that we did with exponents. We want to get this part alone before we decide how we're going to get x out of the exponent spot. So we're going to add 1 to both sides. And then we're going to divide by 3. Now, one way to solve these was to rewrite them with the same base. Are you going to be able to rewrite 1/3 with the same base as 2? No, they're not both powers of 2 or both powers of 3. So that meant we had to do something more difficult. What was our other option? If we can't rewrite them with the same base, how do we solve an exponent problem when we're stuck? When the x is stuck in the exponent and we don't know how to get it out? Change it to a log, okay? So in logs, when we're stuck and we can't get the x out of the logarithm, we change it to exponents. In exponents, when we're stuck and we can't get the x out of the exponent, we change it into logs, okay? So you guys did this 2 different ways. You either rewrote the equation, okay, or you took the log of both sides. So if we rewrote this, okay, we would have log, and what's the base going to be? 2. The base of the exponent is the base of the log, okay? Then you have to decide which part of it goes here and what part goes on the other side. Remember, the answer to a logarithm is the exponent. So the exponent should go over here. What's the exponent from our problem? X plus 2. And that means what should go in here? 1/3. Do I expect you to know what log base 2 of 1/3 is without a calculator?
Yes.
No. Okay? No. So you're just going to leave this and do whatever else you would do to this like it's a number, and this is just going to have to be part of our intercept, part of our answer. Okay? So what's the last thing we have to do to isolate x? Christian? Good. Now, does that 2 combine with the 1/3? No, because this is like all one number, 1/3's part of this logarithm, and 2's not. So you just write it, whatever this is, minus 2. That's what our x-intercept is, okay? And we talked about trying to remember to write these intercepts as points, even though this looks silly because it has like this whole calculation in it. There's my x-intercepts. Okay. All right, so hopefully the y-intercept's a little easier to calculate. Yeah. Huh. One of them has to be a little easier, right? But that's the easy one. I don't know. Okay, so y-intercept, we plug 0 in for x. So we're going to take the same equation. And plug 0 in for x. So this is a little bit better. We don't really have to solve for anything. We don't have to move stuff around. We just have to finish the calculation that's on that right-hand side. And to do that, you need to do exponents before you do multiplication and then addition and subtraction. That's order of operations. So first we need to know what this exponent is. So 0 plus 2 is going to give us 2. And then you don't do 3 times 2 here, right? Exponents before multiplication. So 2 squared will give us 4. 3 times 4 is 12. And 12 minus 1 is 11. Okay? So my y-intercept was 0, 11. Yes, if you already had the graph, you could just pull off the point 0, 11. But most likely on the test, I'll have you graph some and write out your transformations, like it's moving left 2, it's getting stretched, stuff like that. So you'll have those and the graph. And then in a separate section, you'll have different equations that you find the intercepts of. So that's why I want you to be able to do it with the algebra. Does that make sense to everybody? Okay. So your test questions will be like, here's an equation. List to the transformations for me and graph it. Okay. Then here's a different equation. Find the x and y intercepts. Yes, so make sure you're still good at that. That's going to help you with your final too, because your final has questions on it like, which one of these is a translation left to, and stuff like that. Okay. All right, so one more. Let me move it down a little bit again. All right, so graphically, we want to start with our table of values. The parent here is not a parent that we used on the other side. So this is much like you would feel at a test. You're going to have to create this yourself. Okay? But for exponential graphs, what x values do I want to plug in to get the parent function? What does a -1 exponent do to 1/3? 3. Okay. 0 would make it 1, 1 would make it 1/3, and 2 would make it 1/9. Oh, sorry, I shouldn't graph this one. Thank you, whoever was whispering, why is she graphing this right now? Thank you. That helped me. Okay. I appreciate it. Okay, I don't know why I was graphing it. I felt the urge to graph it all of a sudden. Okay, so now we need to do our transformations. Oh, thank goodness it's Thursday, right? Okay, so our transformations. We have a vertical reflection or a reflection over the x-axis. We have a vertical stretch. We're going to the left 3, and we're going up 1. Okay? So the horizontal stuff is just the left 3, and then the vertical stuff, it's being multiplied by -2, and then adding 1. So I'm going to subtract 3 from all of my x coordinates. And then for my y coordinates, I'm going to multiply them by negative 2 and add 1. So 3 times negative 2 is negative 6, plus 1 is negative 5. 1 times negative 2 is negative 2, plus 1 is negative 1. 1/3 times negative 2. So 1/3 multiplied by negative 2 is negative 2/3. Okay? But then I have to take that and add 1 to it. So if I think of 1 as 3 over 3, that means 3 is my denominator, and negative 2 plus 3 is my numerator, which is 1. I did all that work. And then the same idea for 1/9. Okay? So 1/9 times negative 2 would be negative 2/9. And then I have to add 1 to that. So I'm going to think of 1 as 9 over 9. So I'm going to get 7 over 9. And if you're like, Miss Dahl, I don't know what 7 over 9 is. Neither do I, but I know that it's closer to 1 than it is to 0. It's more than halfway there, right? Because 9/9 would be 1. Okay, so that's the best we're going to do. And then our asymptote was normally at y equals 0, is now going to be, because of this plus 1, at y equals 1. So I'm going to put my asymptote at 1. And then I'm going to plot the points, and hopefully they correspond well with this. So negative 4, negative 5. I'm going the wrong way. Negative 3, negative 1. Negative 2, positive 1/3. And then negative 1, 7/9, which is like almost 1. So that corresponds really well because it looks like it's getting really close to that asymptote at 1, but that the curve is going this way. Are you okay with this? All right. So then let's look at our intercepts again. Okay, so your x-intercept, you plug 0 in for y, just like we talked about in the last one. The difference is just going to be getting through the calculation, okay? The idea is going to be the same each time. So we're going to go ahead and subtract 1 from each side. And then do what? Divide by negative 2. You need to get the exponent part alone first, okay? So we're going to have 1/2 equals 1/3 to the power of x plus 3. Can 1/2 and 1/3 be rewritten with the same base? So 1/2 is a power of 2. 1/3 is a power of 3. But you can't rewrite them as powers of anything else that's like a nice whole number like that. So we're stuck. So we're going to write it again in log form. Okay? So log, which piece of this equation is the base? 1/3. And then one of the other pieces is going to go here, and one's going to go on the other side. And remember, the answer to a logarithm is equal to the exponent. So the exponent should go on the other side. What's our exponent? X plus 3. Okay. And so then this is a number. I don't know what it is, and neither do you, and I don't expect you to get the decimal. We're just going to leave it the way it is. And the last thing we have to do is subtract 3. Okay. So our x-intercept is at whatever you get when you do this calculation. Okay, so written as a point. And then our y-intercept, it'll be a little simpler like last time. Okay? You still have to do calculations. I'm not saying it's simple. I'm saying you have to do less work and thinking than the other one. You don't have to transform it to a log or anything like that. So our exponent here is 3. And then we need to calculate 1/3 to the 3rd power. So 3 to the 3rd power is 27. So 1/3 to the 3rd power will be 1 over 27. Then negative 2 times 1 over 27 It'll be a -2 in the numerator and a 27 in the denominator when we multiply across tops and bottoms. And I have to add that with 1. Again, I want to rewrite 1 with a common denominator, so I'm going to think of it as 27 over 27. So 27 is my denominator and 25 is my numerator. Okay? So that means my y-intercept comes out looking like that fraction.